Now get ready to witness a revolution in autonomous driving technology with the work of Alberto Lucchini, Technologist, and Professor Sergio Matteo Savaresi from Politecnico di Milano. In this presentation, Alberto will explore how VI-grade solutions are used to optimize autonomous perception and control. Discover how VI-WorldSim and VI-CarRealTime empower us to enhance scene understanding, streamline model training, and expedite controller tuning.
Okay, thank you. Thank you for the introduction, and nice afternoon for everybody. I would like to start my presentation by telling you a little bit about our project. It's called the MILANO. Actually, who is involved? Politecnico Milano, my university, and the objective is to make a self-driving car that can, starting from the June of the last year, can go around the different cities of Italy, the different type of environments, so urban, extra-urban, suburbs, and highway, and around Italy. And this project is very challenging, and because we made last year Miglia race. So starting from Brescia, we do the round trip going through Rome, and this long journey allows us to place our experimentation in the top right corner of this chart that says that we want to make a self-driving vehicle that is truly multimodal and goes around a different variety of context. To make this journey last year, we took several steps toward the success, and we do the first test traveling across Italy, and here are some pictures with the, let's say, the success of our vehicle, with a lot of people seeing that, and it was a very beautiful, let's say, event. But we want to do more, and later I'll tell you how we can make it. The vehicle itself, it's a self-driving car, and now I'm gonna tell you about the 4 micro areas that characterize this vehicle. So first of all, we spoke about the sensors. So the vehicle has a couple of GPSs, so 2 radar, cameras, and LiDARs placed all around, and you can see it in the car outside. And this sensor allows us to acquire the stream, the camera stream, the LiDAR 3D visualization, and especially also the radar, so you can see the green arrow pointing the movement, the direction of the vehicles that is around the perception of the car. These sensors are then collected and fed through the different type of networks into the computing units. So we can identify 2 types of networks. The first one is the CAN bus network. There are many of them, and they can exchange, let's say, fast and low-level data. And the second one is an Ethernet network that can transport raw data with a lot of weight, a big stream of data, toward what is the computing unit. This computing unit that will compute a series of information that can then be actuated through this series of actuators. So an overlay, a motor that can turn the steering wheel, a motor that can push the brake, and the throttle. The main computing unit in our case is the auto-com board. This computer is very powerful, has a lot of CPU capabilities, GPU capabilities, and networking with the 10 gigabit Ethernet and a lot of CANs. This is the main computing unit that can allows us to run the full stack, the full self-driving stack in real time on vehicle. And the stack is based on ROS2, that is a robotic operating system. And this allows us to be very modular, since we are also a university. So we need to be very rapid into bring a novelty in the car and allowing our students to join the project and be ready since the beginning. The different sensors are then going through the different, let's say, perception stack, localization stack, mixing together into the planning. And the planning then decides which is the best trajectory to be followed, and it's fed into the vehicle dynamic control, then control the actuator itself. All of this is, has the umbrella, and it's under the umbrella of the tactical decision maker that says, yes, this trajectory is feasible, or it's not, there's a red sign or not. So this is very sneak peek of our software, but it's just to give you the idea of what they are doing. To test this big software stack, we need to start through the simulation. The simulation that in our case is based on real-time concurrent that runs VI-WorldSim that is connected to the VI-WorldSim that generates the environment. This environment can be then fed into two different type of, let's say, user. The first one is the self-driving stack. So we can get the environmental data computed back to the main embedded computer on which we are running the full stack of the self-driving car. Or the second one is to simulate what a driver in the car can do. So we have the human driver that can see the visual render of the environment. This simulator can, of course, simulate all the different sensors inside the real car. So we have the low-level one, the GPSs, the IMU, and the actuators, with all the vehicle dynamics that all of you knows very well from CarRealTime. And also the camera, the LiDARs, and the radars from what is VI-WorldSim. You may wonder, OK, big scheme. Do you test it? Yes. We've made a lot of kilometers due to the fact that we need to prove, to do tests on public roads, that we are reliable on our self-driving stack. We've performed 9,000 kilometers of simulation in different weather condition, different type of environment. This is an urban, you may recognize the Gliacco, but also highway and different road types. And this gives us the green light to start our experimentation on public roads. But this is a very big introduction to give you now the focus on which is the topics of today's presentation. So I want to show you the first one. It is the navigation on open roads. So how we can, using the simulator, empower the navigation of this car using what's the region of the street that can be used for the car, of course, so the street itself. And then another deep dive into the twin loop simulation. That is a revolutionary, let's say, approach in which we use the simulator real time in the car to do something special that I'm gonna show you later. So first of all, the problem. We want to reconstruct where our self-driving vehicle can go or cannot. And to do that, we need to start with what the vehicle see. A camera and the LiDARs. Okay? This is the raw information that goes into our self-driving stack. This information has to be processed. The first step is to process the camera. So we need to do a semantic segmentation of the camera, understand where the vehicle can go. In this case, it's the purple area of the image. Okay? But this is a flat image. We need to do another step. We need to go in the 3D world. So we bring inside the LiDAR data, and we fuse it together to have a 3D image. Okay, but the 3D image is not something that can be used in a planner of the street, where maybe it wants to see the street in a top view. Okay, so we need to reconstruct a BEV, a bird eye view reconstruction. So we have 3 steps, and all of these 3 steps are key points of understanding where the vehicle can go. So let's treat it one by one. The first one, the semantic segmentation. The usual approach is to start from a pre-training network. There's many of them, but of course they are lacking of precision on our implementation. So the first step is to add the data to this network and train it again. So we're starting using the cameras, and by hand, labeling the data, but it's very boring. It's very complicated, and it's also prone to human error. So what we do is synthetic data generation using the simulator. So VI-WorldSim gives us the segmented image with the exact pitch position of the camera respect to the one mounted on the vehicle. So we don't need to take the image by ourselves, but we can generate already labeled data with the simulator. And this, let's say, refine very quickly the neural network that are available. Second step is to reconstruct the 3D image. Actually, for this, we go directly with the image plus point cloud of the LiDAR. We do a fusion node, and by some calibration, we can project the image from the, let's say, flat RGB world to the third dimension. So we add the D into the image. And of course, since the image is now labeled, also the label are in the 3D world. But let's say this is, of course, a complicated task, but is not the key point of today. I want to show you how we can generate from the 3D perspective the BEV. So we want to bring the purple of the street from that type of image to something like this. So a view that goes on this top and say, okay, this is the street, this is the line of the boundaries, where the sidewalk and so on. And to do this, we didn't found some previous work that fits our needs. So we need to start from the ground up. And to do that, so we need a lot of data. And to gather this data, we decide to use, of course, the simulator. So we have, to train a network, we need two things. First, the ground truth. So we use the ideal segmented data of the camera that the simulator can provide because it knows exactly all the environment, and the ideal depth camera. So something like this LiDAR, but it's more dense and more precise. Altogether, these combined can generate the ground truth. So the data that is the perfect identification of the street. And then we use the real camera of the simulation and the real LiDAR that can produce the so-called real BEV. So something that has to be, is the data that we can obtain similar to the one that we can obtain from the car. Okay, so the car produced let's say the simulated car can produce the so-called real BEV. I know it's something complex with the naming, but it's the best I can do. And the other one is the ground truth. Combined together, we can train the neural network. I hope that this video clarify better this. So on the left-hand side, we can see what is the true identification of the street with the light gray, where the car can go, and with a little bit darker gray, the lines of the street. And this is the reconstructed BEV. So you can see it's a little bit more, let's say, not so perfectly refined, but it gives us the idea that where the road can go and where we cannot go, okay? And all this information, so the base, the big data that needs to be collected to train a network, for us, is coming from the simulator. So what my colleagues and I will do after this big data collection is to just fix some specific cases to train the network that then it's ready to be put on the car. Okay, so the big quantity of data, the data set that train the network is coming from the simulator, and just with some tweak, minor tweak of this data set, we can have a functioning neural network for our vehicle. And you may wonder, okay, can you see it works? Yes, actually, this work is has been placed in a paper right now. It's under revision, but it goes through all the different steps I just explained to you, and this is the first thing. So the semantic segmentation on 3 cameras works live on a high FPS count, and has been tested on open roads. So this is the first step of the one I just presented. And you can see the purple of the street, the white of the lines, and this is Bergamo, and it's quite working. And the second one is the real-time generation of the bird eye view. So on the left side, you see the pictures coming from the cameras, segmented. Then the, let's say, middle, in which you can see the LiDAR propagation and what the LiDAR can see. And then the third one is the true bird eye view reconstruction of the street. Okay. So of course it's a little bit speed up the video, but you can see that once we take the road, the straight road, it's very clear that in white we can represent the path where we can go with the car. In black, the boundaries. So as we approach the cross, you can see there's the option of the two streets that goes around, and it's, I hope it's quite clear that it shows where the vehicle can go. Okay, the roundabout. And all of this has been possible thanks to the big data that we acquire, and we train this network to be ready to identify complex scenarios such as roundabout, T-junction of the streets, and all these cases have been like trained. The network has been trained with the data coming from the simulator. Okay, and that's for us it's a quite interesting achievement. Okay. Going on, we can switch to the other topic. So the twinning the loop simulator. Twinning the loop is something more related with the, let's say, low level of the vehicle dynamics. And to do so, we need to break down a paradigm. So we have the real vehicle that can be modeled as a digital twin, so the VI-CarRealTime digital twin that we know well, or with explicit control-oriented formulation. That maybe it's more clear, but they are have a region of domain more defined. We can write down the equation of longitudinal dynamics, vertical dynamics, but it's complex to have a complete view of the vehicle. And so we want to take the best out of the digital twin, but of course it's heavy and has very complex, no? In our vision is we can let's say use this complex digital twin in two ways. So the filtering or the control. For filtering, we can use the digital twin to simulate internal states of the vehicle that are not measurable in the real one. Okay, and for control, we want to use the digital twin to again see states that are not visible in the real one, and based on that, compute the best control action for the real one. So use the simulation to understand which are the best control action that we can take, and then fed the real vehicle. But I'm going to show you later how. So the filtering has these advantages. So it's already available because when you build a vehicle, or well, today when we create a prototype, so a virtual prototype for building a vehicle, you have already the digital twin. And with this digital twin, you are ready. You have already all the information about your vehicle. So it's already available. Has an high accuracy because it's a very complex model that has all the states necessary to define the dynamics of the vehicle. And of course, estimate all the states because you know exactly each part of your vehicle. The downward is that it's a black model, so it's very complex. You have not all the equations. With that, you can compute the estimation, and then based on that, you have the possibility to control all the state. And this results into very good filtering performance of the state of the vehicle. About the control, same ideas, but you now have the information inside your vehicle, the states, to control the real one. And again, this allows us to have better performance, even better than the reference one. So the MPC is the purple line, and the TIL has better performance in controlling ABS result. Okay. I know it's very quick, but just to give you the idea of this work that we are done in our research topic. Going on, just last slide about what is the scaling up of this project. So, 2022 we start with the project. Last year we made the Miglia with the car you can see outside. We are now taking the next Miglia, so in a couple of weeks, and we are planning to scaling up. And with us, with the great increase of the project, also VI-Grade is following us, giving much more presence in our, let's say, long-term view. So from the dynamic simulation up to the perception that today I show you, and more on the next challenges. Thank you for your attention, and hope to have a nice evening. Thank you.